We use numbers all the time, every single day, right? From checking the clock to counting our change. But what if I told you that under the surface, there's a whole hidden universe of numbers with families, rivals, and some really wild, untamable members? Let's take a look. So let's just kick things off with this big question. Are all numbers really created equal? I mean, on the surface, a 2 is just a 2, right? But it turns out there's this incredible hidden world of classifications and categories that makes the universe of numbers way more fascinating than you might think.
Okay, so to really get this, let's imagine something I like to call the number family tree. We're going to start at the very bottom with the absolute basics, the first numbers any of us ever learn as kids.
And first up on our tree, we've got the natural numbers. These are your classic everyday counting numbers. 1, 2, 3, 4, and on and on. If you think back, these are literally the first numbers you ever learned. So simple, so intuitive, but they are the bedrock for everything else to come. Now, what happens when we introduce a totally revolutionary concept? The idea of nothing. That's when you get whole numbers. All we did was add 0 to our counting numbers, but suddenly our system is way more powerful. It seems like such a tiny little addition, but it was a massive leap forward in what math could do. And this is where things really start to open up. When you take all those whole numbers and you add their opposites, the negatives, you get the integers. All of a sudden, we can talk about things like debt, or temperatures below freezing, or even just moving backwards. Our little number toolkit just got a serious upgrade. So we've got our integers, which feel pretty complete. But this is where the number family tree forks, and it's a huge split. We're about to step into what's called the Great Divide, this fundamental split between two very, very different kinds of numbers, the rationals and the irrationals. And what's so cool about this is how it lays out the difference. On one side, you have rational numbers. Think of these as the well-behaved, predictable ones. You can always write them as a nice, clean fraction. And when you turn them into a decimal, they either stop, like 1/2 just becomes 0.5, or they repeat in a neat pattern, like 1/3 becomes 0.333 forever. But then you have the irrationals. These are the rebels. You can't write them as a simple fraction, and their decimals are just pure chaos. They go on forever with no pattern at all. So where do these wild, mysterious, irrational numbers even come from? Well, believe it or not, one of the most common places they pop up is in the world of square roots. So let's dig into that mystery for a second. See, some square roots are perfectly neat and tidy. We call these perfect squares. The square root of 16 is just 4, because 4 times 4 is 16. The square root of 81 is 9. Easy. These are rational, clean, simple integers. No problem. But what happens when you try to find the square root of a number that isn't so perfect? Like, what about the square root of 7? This is exactly where things get, well, irrational. And wow, look at that. This is the perfect example. The square root of 7 is this long, chaotic, unending decimal. There's no pattern, it never repeats, it just keeps going and going and going into infinity. This right here is a classic irrational number. You just can't pin it down to a simple fraction. Okay, so things are getting a little messy, right? We've got these nice, orderly integers, and then we have these chaotic, endless irrational decimals. How do we make sense of it all? How do we bring some order to all this beautiful mathematical chaos? Well, it turns out there's a really simple, elegant tool for that. The number line. It's the ultimate organizer. It's this beautiful visual where every single number we've talked about, natural, whole, integer, rational, and yes, even those wild, crazy irrationals, every single one has its own unique address, a very specific spot on this line. But hold on a second. If a number like the square root of 28 goes on forever with no pattern, how in the world are we supposed to find its exact spot on the line? It seems kind of impossible, right? But there's actually a very clever trick. See, you don't actually have to chase that endless decimal. Instead, you can trap it. All you have to do is find the perfect squares on either side of 28. Well, we know 25 is a perfect square, and the very next one is 36. So since 28 is caught right there in between them, that its square root has to be caught between their square roots. The square root of 25 is 5, and the square root of 36 is 6. And just like that, we've pinned it down. We know exactly where it lives on the number line, somewhere between 5 and 6, without ever needing to write out that infinite decimal. Pretty cool, right? Okay, that's all really fascinating, but let's be real. So what? How does knowing about irrational numbers actually help us in the real world? Well, it turns out this whole system is the backbone for how we measure and make sense of everything, often through a simple process we use all the time: unit conversion. Let's take a super simple everyday problem. Your friend says they'll meet you in 3.5 hours. Okay, but how many minutes is that exactly? This is a classic unit conversion, and our number system gives us a foolproof way to figure it out. And there's this super simple 4-step recipe for getting it right every time. Step 1, know what you have. In this case, hours. Step 2, know what you want. Minutes. Step 3, find the bridge that connects them, the conversion factor, which we all know is 60 minutes in an hour. And finally, step 4, you just set up the math so the hours unit cancels itself out, leaving you with just minutes. And this little process works for everything, not just time. I mean, look at temperature. Whether you're going from Celsius to Fahrenheit or back again, it's really just a matter of plugging your numbers into the right conversion formula. It's a reliable system you can use over and over. So, back to our question about the 3.5 hours. Using that simple 4-step method, we multiply 3.5 by 60, and boom, we get our answer: 210 minutes. It's a practical, real-world problem solved with a clear, logical system. And honestly, that's the whole point. We've gone on this little journey from the simplest counting numbers we learned as kids, to the idea of zero, to negatives, and all the way into the wild world of these infinite irrational numbers. And what we see is that this whole elegant system is what allows us to measure, to calculate, and really, to make sense of the world around us. And here's the big takeaway from all of this. Understanding this stuff isn't just for a math class. It's like a superpower. It really is. It helps you navigate everything from following a recipe in the kitchen to understanding a huge scientific breakthrough. It's the language our world is written in. So I'll just leave you with this final thought. We started with something as basic as counting, and we uncovered this whole universe of complexity hidden right beneath the surface. And it just makes you wonder, if numbers hold that much hidden depth, what else are we overlooking every single day?